This is where life. Someone is mission.
That is. Where is he? Sandeep Mishra. He is the. Hi Sandeep, how are you? Sandeep, are you hearing me? Oh, he has to only type,
Yes.
Session. Hello everyone, welcome to this live session. If you have any questions, please type in the chat box. Hello Sandeep, how are you? Sandeep, are you there? Are you listening to me? Okay, good. Yeah, I know that. That's what this here NPT office told me. Others can only type, only I can speak. Others can only hear me, and I can see your typing.
Ankit, sir.
Aniket.
Ankit. Sir, you got a question?
He did not get the answers for assignment 2. It was uploaded?
Yes, sir, it was.
Yeah, Aniket, I am told by NPTEL office it is already uploaded. Answers have been uploaded. If you have not received it, anyway, after this session, we can again make sure that it will be uploaded and you will get the answers. You have already said yes.
Okay.
So, Aniket, you can send an email. I'll see that if the answers have not been uploaded, I'll see that everything is uploaded again.
Email ID.
Also, send your email ID by email. Anyway, once it gets send the email, I will know. Okay, Aniket, your question on 14N resonance. It is because 14N is a quadrupolar spin and it relaxes very fast. The lifetime in the excited state is too short and relaxes so fast, it simply goes by uncertainty principle. There is a spread in the energy states, both high and lower energy state. As a consequence, you are going to get a broad peak. So it is because of N14 being a quadrupolar spin and it has a short lifetime in the excited state. That is the reason why N14 resonances are usually broad. Are you okay? Is it clear for you, Aniket? Okay, I will ask the NPTEL office to upload it, and whatever the assignments which have been submitted till now, for all of them, answers will be uploaded. I will tell them. It will be uploaded soon. Usually, the duration of the excitation pulse, Aniket, you are asking, it is depending upon the nuclei of your interest. Usually, for protons, 90-degree pulse will be of the order of 4 to 5 microseconds. And if it is some other nuclei like carbon 13, etc., it can be a little bit more, of 8 to 9 microseconds or 10 microseconds. Usually, it is of the order of few microseconds. Is it okay, Aniket? The pulse width, duration of the excitation pulse is of the order of few microseconds. In any case, it may vary with for nuclei to nuclei, but of the order of 5 to 10 microseconds, 15, 20 microseconds. That's what you can think. Okay, Aniket, this is the selection rule you are asking. When the change in the magnetic quantum number between any two states, spin states or energy states, is +1 or -1, they are all called single quantum transitions and are all detectable transitions. So transitions can be detected when there is a change in the magnetic quantum number between any two spin energy states is either +1 or -1. For example, consider spin half nucleus. It has two energy states, plus half and minus half. You take the difference between plus half and minus half. Half minus of minus half, it is 1. So that means you go from alpha to beta states. That is allowed transition. Come from beta to alpha minus half plus half. That is again minus 1. That is also allowed. So essentially, if you take one single spin, transition from alpha to beta and also from beta to alpha, both are allowed because the change in the magnetic quantum number between these two energy states is either plus 1 or minus 1. If you have more number of spins, you can find out what are the possible spin states, like depending upon the orientation of the nuclear spins. You know that alpha, beta, alpha, all those things depending upon number of spins you have, you can find out what are the total number of spin states available or energy states and find out what is the difference between the magnetic quantum number between any two energy states, and if it is plus 1 or minus 1, you can say they are allowed transitions. Okay, Nizamuddin, please tell me what is your problem? What is your question? Aniket, are you clear with the transition? You are asking about the selection rule. Aniket, please respond. Is it clear for you? Okay, Nizamuddin, you have any questions? Please type. Okay. Aniket, I think this question you asked in the email, for which you have also answered, I guess. I don't know whether you or somebody asked the question. See, always the direction in which you apply the pulse for a particular axis, that is the axis of rotation. Supposing you are applying 90-degree pulse along x-axis, that is, you are rotating the magnetization along x-axis. If you apply along minus x-axis, you are rotating along minus x-axis. And always you have to apply right hand thumb rule. That means if you are applying along plus x, your thumb will be in that direction, and then you can see which is your curly finger. The curly finger direction in which it shows, that shows the direction in which magnetization is going to be tilted. So you can find out now if you apply 90-degree pulse along minus y axis, and of course you have to say which is the minus x axis and which is the, I have to write a drawing. If you give me time, I'll show you here. For example, I cannot write here, unfortunately.
One excuse me. Is it a minute?
Okay. Aniket, let us consider. Let us say this is x-axis, this is y-axis, this is z-axis, and your minus y-axis. Your question is like this. That means you are applying pulse in this direction. This is your thumb. Okay, and then you are going to tilt the magnetization in this direction. Okay, so it will be tilted. Imagine if it is, you have to take plus y above the plane, above this plane, and minus y is back side of it. If it rotate like that, that means it goes to this side. Imagine, I'm sorry, if it is minus y, if you are going from that side, okay, that's correct. So this is z-axis. You are rotating like this, so it has to come this side. Just imagine a three-dimensional figure. Let me write minus y this side, plus y. This is x. Then this cannot be x. I'm sorry, this cannot be written like that. Okay. Well, I think this is the way you have to write. So you take this as a minus y axis, and you are applying the pulse along this axis. Put your thumb impression like this. Create a, imagine a three-dimensional figure. Okay. So magnetization has to tilt like this. So it has to go along this axis.
Yes, sir. So you want to explain in
No.
video?
No, okay. We'll go to video. Aniket, are you there? Aniket, I think, are you able to follow me? See, you have to imagine a three-dimensional x, y, and z axis. Just remember, the direction in which you are going to apply the pulse is the axis of rotation. If you are applying pulse along minus y axis, you are rotating along minus y axis. Imagine it is a right hand rule. That is, thumb of your right hand is in that rotation axis, and find out which is the direction in which the curly fingers goes, and towards that axis the magnetization tilts. I don't know how to show it to you in a three-dimensional figure here. I hope you did understand. Okay. Okay, imagine like this. You see the video. Let us say this is the minus y axis. I am rotating about this axis in this direction. This is my right hand finger, thumb, and then when I rotate like this, it has to come like this. If this is minus y axis, opposite is plus y axis, magnetization is like this. Okay. If this is plus axis, this is z axis, x axis must be somewhere here. So if I rotate like this, the magnetization which is along z axis will come towards this side. If this is minus y axis, this is plus y axis, and this is x, this is minus x, it will come to this side. Are you imagining the three-dimensional figure? Okay, Brijesh Yadav is asking three-dimension. Just now that's what I said. Okay, do you have another pen? Okay, I have another pen. See here, this is the magnetization. This is plus x axis. If you apply pulse along this axis, that means you are rotating along this axis. Magnetization. This is the axis of rotation. But you see, magnetization is along this axis. You have to consider this is my right hand. This is the thumb. So if I rotate along this axis, that means my finger is pointing towards this. So it has to go in this direction. Is it clear for you? If this is plus x axis, I am applying along this axis. That means I am rotating along this axis. I rotate like this. The magnetization which was along z-axis will come here. If this is x, then this has to be y, this is z. That means it is going towards minus y. Is it clear for you? Let me repeat. This is z-axis. Magnetization is along z-axis. This is your plus x-axis. I assume I am applying the pulse along plus x-axis. That means I am rotating on this in this axis. This is my axis of rotation, and I put my thumb of the right hand on this axis. Now let me see. You see clearly my finger when I rotate. Curly fingers goes in this direction. That means the magnetization will rotate in this direction. For a 90 degree, if I rotate along plus axis, and this is y, this is plus x, it has to go to minus y. You understand? So if I rotate along plus axis, it is going like this. Exactly, you can imagine what is going to happen if you apply along plus y, if you are applying along minus y or minus x like that. So minus y means it is to, you have to, if this is plus y, you have to think of minus y. It is difficult for me to imagine three-dimensional space from the other direction. That's why I took plus x to explain. You can imagine you create a three-dimensional XYZ axis, and then you can see yourself by rotating which direction it goes. Okay, always remember, axis in which you are going to apply pulse is the rotation axis. You have to put your thumb of the right hand on that axis. Assume you are rotating the thumb. Is it okay for Brijesh and Aniket? Brijesh, are you okay? Aniket? Okay, Aniket says okay, it's very good. See, if you have any other questions, you can also type in the question in the email, in your ask the question in your website on the Swayam website. You can type your questions in the email. We will try to answer as soon as possible. See, email ID you are asking Aniket. You don't have to send the email to me. Your NPTL would have told you how to ask the questions, right? On the website. In the Swayam website, you can also type the questions. Like all other participants are typing the questions there. You can type. The email ID is not my email ID. That is there on the website, I think. If you log into this course, all the information should be available on this website. Correct? Email?
Yeah. One minute, sir.
Okay, if you want, if you have a difficulty in typing in that website, you can also send to my email ID or Sandeep's email ID. One of us, definitely you will get the answer. My email ID, of course, in the PPTs, in the videos, every video when I start that email ID is given. You can use that email ID. If you see my lecture videos, in the very beginning itself, with my name and address, email is also given. You can send your questions to that email. Sandeep, can you type your email ID so that if they want, they can contact you? See, if you have any specific questions, you can ask Sandeep. Sandeep is an expert in NMR. He can answer all the questions. So you have your his email ID. You can type in this chat box also, Sandeep, your email ID. Those some of the people who have not got your email ID, they can note down.
That like
Go.
oops. Any questions?
Okay. See, Aniket, in thermal equilibrium with random phase approximation, the bulk magnetization MNAS is in equilibrium. It is along z-axis, right? Which is along z-axis, and it will be in thermal equilibrium. It is stationary. Okay. What that I have already discussed in detail about random phase approximation. Consider one magnetic moment. One magnetic moment. That is, you can consider that as a vector. It has three components. You can consider the three-dimensional vector. Magnetic moment, I call it as mu. It can be mu z, mu x, and mu y. Okay. There are several millions of magnetic moments like this. All of them will be there, and along the z-axis, what happened? They all will be aligned along this axis. Not exactly z-axis. There is some angle, no problem. Consider they are all along z-axis. In the x-y, they are all oriented in different directions. If you take an ensemble average along xy plane, if you have one vector along this axis, they have another vector in the equivalent opposite direction of the same magnitude. If a vector of this magnitude is in this direction, you can find another vector. There is an equal probability to find it in the opposite direction. The vector addition in the xy plane is then 0. Similarly, if you take infinite number of vectors in the xy plane, their x components and y components in that plane, if you take the ensemble average, it is going to be 0. However, along z-axis, there is no averaging because most of the spins are along this axis. All the magnetic moment vectors are along this axis. The vector addition is a sum then. They all will be added up. Okay. Now, consider another vector which is in the direction opposite to the magnetic field. Again, it can be resolved into three vectors. X, Y, and Y component similarly because of random phase approximation gets averaged out. The magnetization along minus Z again get added up, all the vectors. But as I said, there is more spins in the direction of the field than opposite to it. So if it and consider the vector addition, there is a small excess amount of this in this direction than this. Again, take the difference between vector sum of the magnetization, all the magnetic moment vectors, which is called magnetization along z-axis and minus z-axis. There is a small excess along z-axis. Take the difference. And that difference, that excess population, will be along z-axis. This is called magnetization, bulk magnetization. And bulk magnetization, you can consider like a tiny magnet which comes because of the vector addition of all the magnetic moment vectors along z-axis, and in the random phase approximation, the xy plane, their component values goes to sum of all their vector addition will go to 0. And this is always stationary in thermal equilibrium. Is it clear for you, Aniket? Okay. This question, for which I have already answered, the NMR transitions are detected with two energy states. Just now I answered. I don't know who asked the question, Aniket or somebody. And this is the difference in the magnetic quantum number between two energy states is either +1 or -1. I already explained, taking an example of single spin plus of or minus of states, beta and alpha states. The difference between beta to alpha is -1. Difference between alpha to beta is +1. So the transitions between alpha to beta and beta to alpha both are allowed, because the change in the magnetic quantum number between these two states is either +1 or -1. If you have more number of spins interacting, take for example 2 spins, each spin can have alpha and beta, two possible orientations. So now there are 2 spins, consider both of them can be up, both of them can be down, one up and one down, or this up and this up. 4 possible combinations. When both are up like this, it is plus half and plus half, it is +1. When both are minus like this, it is -1. This is plus half and minus half is 0. Minus half and plus half is also 0. So now there are 4 energy states. Write down the total magnetic quantum number for each of the states. It is -1, 0, 0 and +1. Now find out the difference between these energy states. What is the difference in the magnetic quantum number? -1 to 0 is allowed. -1 to this 0 is allowed. 0 to +1 is allowed. Similarly, reverse, +1 to 0 is also allowed. Only thing is -1 to +1 is not allowed, because it is going to be -2, or if you go reverse way, +1 to -1, it is going to be +2. That is not allowed. Similarly, alpha beta to beta alpha, that is 0, 0, that is also not allowed. So the only transition that are allowed are the one where the change in the magnetic quantum number between two energy states should be either +1 or -1, be it a single spin or many spins which are interacting. So you have to find out what is the total magnetic quantum number for each energy state, and you can easily calculate it. Are you okay? Somebody, I don't know what is his name, his DC is written. Mr. DC, I hope you have understood. Is it clear for you? That's fine. Okay, very good. Yeah. Correct. Sandeep has already written the answer. You people can write down. It is +1 or -1. Sandeep, can you please type your email ID in the chat box? Somebody was asking. Aniket or somebody. See, participants, please note, we already have, we are left with only 10 minutes, I guess. So if you have any questions, please ask now, because after 10 minutes, as per the schedule, NPTEL will close it down. Will shut down this session. Okay. Apparently, Sandeep has already given the email ID. I hope all of you have got it. You have also noted on my email ID from the first slide of the lecture videos. You can email to any of us. Okay, Aniket, for your question of resonating frequency for nitrogen 15, it goes by what is called gyromagnetic ratio. At 14.1 Tesla, if the precessing protons precess at 600 megahertz, gamma of nitrogen 15 is 10 times approximately. Exact number I am not telling you. You can find out from the gamma. Approximately it is 10 times smaller. That means the resonating frequency of nitrogen 15 in the magnetic field of 14 Tesla is 60 megahertz. Are you okay? Is it clear? Okay, Aniket, you want me to repeat? You know, at a 14.1 Tesla of magnetic field, protons you have written precise at 600 megahertz. Let us say gamma of proton is some value, gamma. Nitrogen is 10 times smaller, nitrogen 15 gamma. That means it's gamma by 10. That means resonating frequency is 60 megahertz. Now you are asking this precision, sense of precision. That is different. You asked me about the frequency and precision. Frequency is 60 megahertz. Now if you want the sense of precision, please note nitrogen 15 has a negative magnetic moment. It means it precesses in the direction opposite to that of protons. Proton and nitrogen, they have opposite magnetic moments. Proton has a magnetic moment, its magnetic moment is positive, nitrogen 15 is negative. So the precision, direction of precision or sense of precision, if proton is this way in magnetic field, nitrogen 15 goes in the opposite direction because of negative magnetic moment. Not only nitrogen 15, and all the nuclei whose magnetic moment is negative precesses opposite to that of protons. All those which have positive magnetic moment or gamma is positive precesses it this way, negative will precesses in the opposite direction. Is it okay, Aniket? So one person is asking assignment answer, please send. 1 second, be on the line. Now you can tell who is to, let it be there, who is to upload the answers.
I'm not aware of it.
Can you find out and tell me later?
Sir.
Okay, I have asked the NPTEL person here. He is going to find out. I think they are uploading. Otherwise, I will request Sandeep. He is going to upload it for you if it is to be done. Don't worry. It will be done soon. All the answers are ready. Only it is a matter of uploading. It can be done anytime. But I don't. Are we uploading the answers or questions also? Only questions,
No, sir. I think they will answer to the questions by week.
Correct.
So I think only 1 week or 2 weeks has been over, right?
Okay.
So for only
Afterwards,
2 weeks,
we'll upload the answers also.
yeah, I think they will give the
Okay,
answer.
fine. It is sorted out by NPTEL office here. Okay, so all the answers for your questions will be uploaded. Whatever has been completed, whatever the questions we have been given, assignment given, and because Sandeep has already given a very clear answer. See, the exact ratio is gamma is 10.137 times smaller than that of 600 megahertz. You calculate then what is the resonating frequency. And as I said, it precises in the opposite direction. Sandeep has written a very clear answer. Please write down or take a photo of this, snapshot photo of this one. It is a very clear answer and accurate answer he has given you.
Sir, I just checked with the NPTEL staff. So they said they are telling answers will be uploaded by TSA.
TAs will
And
upload the
TS,
answer. Okay. So NPTEL office confirmed. Sandeep is going to upload the answer. Don't worry. But
So
you share the answers to him.
is it a repeat or rerun, sir?
It is a repeat course.
Repeat. 1 minute. Okay, sir. As this is a repeat course, they will announce it soon.
Who?
NPTEL office.
Okay. So
If
it is
it is
now there's
rerun
a.
only, if it is rerun, TA will be uploading. If it is a repeat course, from NPTEL side, they will be
Okay,
announce it soon.
we got the clarity. All the answers will be uploaded by NPTEL office it's only. So don't worry, Sandeep, you don't have to worry. NPTEL office will upload the answers and also questions, both. Assignments and their answers will be uploaded by them. Sandeep, you don't have to worry right now. Okay, I'll announce it.
Yeah.
Hello? I think the time is up. NPTEL office wants to close this session. And if you have for any other questions, as usual, you know how to ask the question using that Google form or whatever that to the Swayam website, or you have now email ID of mine and Sandeep, you can send the email to me. So with this now NPTEL is closing down this live session. Thank you very much for all of you for participating and asking questions. So we will keep interacting further later. Okay. No, Sandeep, your email is still not visible. You have written, but it is not visible here. Okay, thank you all participants. and you are going to get the email ID. If you want, if you are not able to see the email ID of Sandeep, which is given, if it is not visible for you, don't worry. When you send me email, I will write to you about his email ID also. Thank you very much. We'll close this session now. Thank you.